Intro Chemistry, the rate of a chemical reaction. The rate or speed of a chemical reaction can be increased by altering several different factors, such as concentration of reactants, temperature, pressure, surface area of solid reactants, and the presence of a catalyst. Let's spend a minute on each one of these. Catalysts. The most well-known example are the automobile catalytic converters. They contain porous, inert ceramic material that's coated with a thin layer of platinum. The platinum catalyst speeds up the conversion of unburned fuel, hydrocarbons, that would otherwise exit the exhaust, converts them into CO2 and water. In another section of the exhaust, another catalyst, rhodium, speeds up the conversion of NOx and carbon monoxide to nitrogen and carbon dioxide. So when catalysts speed up chemical reactions, they are not consumed. Surface area of solids. Wood burns, but sawdust explodes in air. Finely divided steel rusts much quicker than a chunk of steel because oxidation takes place at the surface. With greater surface area, the reaction rate increases. The pressure of a gas. A chemical reaction occurs only when molecules physically collide. If we increase the pressure of a gas, it decreases its volume. That's Boyle's law. And that brings its molecules closer together, and therefore there will be more collisions per second, more per unit time. How about temperature? Hotter molecules move faster. They collide more frequently, and they'll collide harder. Steel rusts faster in hot weather than in cold. Another catalyst, salts, on winter roads act as catalysts carrying electrical charges to speed up rusting or oxidation reactions. And finally, concentration. A higher concentration means more molecules in a given volume, and that would be, therefore, more collisions per second. In this experiment, the effect of reactant concentration and temperature will be determined. We'll use the reaction between sodium thiosulfate, Na2S2O3, and hydrochloric acid, HCl. The products, sodium chloride and water, are colorless. We won't see them. Sulfur dioxide gas is also eliminated. It's colorless. We won't see it, but we will smell the faint odor of it. But solid sulfur, solid elemental sulfur, will be seen. It's a pale yellow or cream-colored, finely divided precipitate, a suspension, a turbidity. And we can view the progress of the reaction by monitoring or viewing the gradual precipitation of sulfur. Specifically, how we'll do this, the letter X, printed large and bold on a piece of paper, will be placed under a flask of the solution. Viewed from above, the time elapsed for the sulfur precipitate to completely obscure the X will indicate the rate of the reaction. Let's take a look at this reaction. In the first part of this experiment, we'll be looking at the effect of concentration upon rate of reaction. So here's what we need. On the left side, you see a solution of 0.25 molar sodium thiosulfate, a bottle of water, and some graduated cylinders. On the right side, we have 1 molar HCl and a 5 ml dispenser. In the middle, there's an Erlenmeyer flask, a stopwatch, and a piece of paper with an X marked on it. And that's all we need for part A. In this first test, we're using 50 milliliters of 0.25 molar sodium thiosulfate. We won't add any extra water this time. Here is 5 milliliters of the 1 molar HCl. We start the stopwatch as soon as we add the acid, and we'll stop it when we can no longer see the X. Okay, about 19 seconds. This time we'll use only 40 milliliters of thiosulfate, 10 mils of water, and then 5 mils HCl. That'll bring our total volume to the same total volume, 55 mils. But our concentration of thiosulfate will be lower this time. Now this should take a little longer. Our final concentration is our initial concentration, 0.25 molar, times the dilution factor. About 23, 24 seconds. This time we add 30 mils of thiosulfate, 20 mils of water, and 5 mils of HCl. Again, our total volume will be 55 mils, but the concentration of thiosulfate will be lower. So our final concentration will be our initial concentration, 0.25 molar, times the ratio of the dilution factor, which is 30 mils over 55. We diluted 30 to 55 mils. That ratio is roughly 3/5 or 0.6, so our final concentration is approximately 60% of the initial concentration. So the reaction is slower. So I'm measuring 31. I'm going to add another second. I think I was a little quick on the stopwatch, so I'll say 32 seconds. Alright, this time only 20 mils of thiosulfate and 30 mils of water. Five mils of HCl. Our concentration will be lower still now. The reaction should take longer. So our final concentration will be the initial concentration, 0.25 molar, times the ratio of 20 over 55. That's roughly 20 over 50, or 0.4, so it's about 40% of the initial concentration. So our reaction time will be longer again. Jumped the gun a little bit on this, so I'm going to add about 3 seconds to that one. 45 seconds. Alright, 10 mils of thiosulfate, 40 mils of water, 5 mils of HCl. Total volume will be 55. What's our final concentration going to be? It's going to be the initial concentration, 0.25 molar, times the ratio of the dilution factor, 10 over 55. Now I've sped this up a bit. I'll slow it down to real time before the reaction is complete. Getting close. There, it's real time. Okay, a little bit trigger happy there. It's hard to see through the camera. I'll call that 2 minutes and 5 seconds. Alright, part B, we're going to keep the concentration constant, but now we'll vary the temperature. The composition will be the same as the last test we just did. 10 mils of thiosulfate, 40 mils of water, 5 mils of HCl, grand total of 55 mils. And our first run at this composition was done at room temperature, which was 22 degrees Celsius. We're going to heat this up about 10 degrees each time. Alright, so this looks like about 32 Celsius. Should be a little bit faster than the last one. As temperature goes up, reaction rate increases, reaction time will decrease. We were like 2 minutes and 5 seconds at room temperature, 22 Celsius. At 32 Celsius, okay, so I've sped this up a bit. I'll slow it down as we get closer. A little quick again. It's difficult to see with the camera compared to the computer. I'm going to add a few more seconds to this. Alright, I'm going to call that 1 minute and 10 seconds. Alright, we've heated this one to 42 degrees Celsius. Alright, 31, I'm going to call that 32 seconds. And at 51 degrees Celsius. Okay, I'm going to call that 22 seconds. Last one will be at 61 degrees Celsius. This should be the fastest. About 14-15 seconds. Okay, that's all we need. Let's go to the procedure and see how we're going to do these calculations. Lab report requirements. For part A, we kept the temperature constant at 22 degrees Celsius, and we changed the concentration. So you need to determine the concentration in moles per liter of each of the 5 different sodium thiosulfate solutions tested. Once you have that, plot these first 2 graphs. The first graph has concentration in molarity on the y-axis versus time in seconds on the x-axis. So as expected, as the concentration decreases, the reaction time increases. That's inversely related. On the second graph, again plot concentration and molarity on the y-axis, but this time on the x-axis plot 1 over the time. 1 over the time in seconds is the rate. And then we see that as the concentration increases, the rate increases as expected. For part B, we kept the concentration constant but varied the temperature. So we have temperature this time on the y-axis and rate again on the x-axis. We can see that as the temperature increases, the rate of the reaction increases as expected. Now these graphs that I'm showing you are not for the data that I recorded in this experiment. Plot the data from this experiment. It will be similar, but it's not exactly the same as this. On the data and results sheet, you need to fill in all the data in the same way as is listed here. Let's take a look at it. In part A, we started with 50 milliliters of 0.25 molar sodium thiosulfate. We added no water, but we added 5 mils of HCl, so the final volume was 55 mils. So 50 diluted to 55 means that the dilution factor, the initial volume divided by the final volume, is 50 over 55. 50 over 55, and that's 0.91. So since we increased the volume, therefore the concentration will decrease by the same ratio. So 0.25 molar times 0.91 is the dilution factor. Our final concentration is 0.23 molar. So basically we're saying by increasing the volume from 50 to 55, the final volume is only 91% of the initial volume. Now the time for this reaction took 19 seconds. You can record that. In the second case, we started with 40 mils of 0.25 molar sodium thiosulfate, and we added 10 mils of water and 5 mils of HCl, so the final volume was 55 mils. And going from 40 to 55, that's our dilution factor. 40 over 55 is 0.73. The final concentration is 0.18 molar. And for this, we've measured a time of 24 seconds. I'll give you the rest of the times and you can calculate the remaining concentrations the same fashion. 32 seconds was the reaction time for 30 plus 20 mils. In the fourth example, 20 mils of thiosulfate plus 30 mils of water, that took 45 seconds. And in the fifth example, 10 mils of thiosulfate plus 40 mils of water, our reaction time was 2 minutes and 5 seconds, which would be 125 seconds. So for part B, we used the solution 10 plus 40, and we'll use that first data point right here. That was at room temperature, which was 22 degrees C. The time for that was 2 minutes and 5 seconds, which we said, or 125 seconds. Then we heated it up to 32 degrees Celsius, and we measured a reaction time of 1 minute and 10 seconds, or 70 seconds. At 42 degrees C, our reaction time was 32 seconds. At 51 degrees Celsius, the reaction time was 22 seconds. And at 62 degrees Celsius, the reaction time was 14 seconds. So please fill out the data just as it's shown here. I would recommend that you watch the remainder of the video that shows a demonstration of dilutions and dilution calculations. It's really important that you're able to solve problems by logical solving methods rather than memorizing formulas. It'll translate to bigger things than just this lab. You'll use that in many different contexts in your job. So take the time to make sure that the process is logical for you to follow. Don't memorize formulas. You'll thank yourself for it many times. Dilution calculations that you'll get right every time. Start with 100 mils of water. I'm putting in 2 drops of food coloring. What's the concentration of this solution? 100 mils of water plus 2 drops of food coloring. Well, that would be 2 drops per 100 mils. If I multiply numerator and denominator by 10, I can say that's 20 drops per 1,000 mils, or 20 drops per liter. That's my initial concentration, 20 drops per liter. Now we'll perform some dilutions with it. We'll take a 20 ml aliquot. An aliquot is a portion of our 20 drop per liter solution. We'll keep it in beaker 1 as a comparison. I'll take another 20 ml aliquot of our 20 drops per liter solution and put it in beaker number 2. But in beaker 2, I'm also going to put another 20 mils of water. So the volume is increased from 20 mils up to 40 mils. Since the volume increased by a factor of 2, the concentration decreases by a factor of 2. Those volumes, 20 and 40, can be combined to make what's called the dilution factor. You can say the dilution factor is either 20 over 40, which is a half, or you can say it's 40 over 20, which is 2 times. Use that dilution factor to calculate the final concentration. Take your initial concentration, 20 drops per liter, and multiply by 20 over 40, which is a half, gives you 10 drops per liter. Your final concentration is 10 drops per liter. Or if you prefer, take your 20 drops per liter and divide it by the dilution factor of 40 over 20, divided by 2, and you have 10 drops per liter. Don't memorize a formula, just make sense of it. You'll get it right every time. Alright, beaker number 3. Again, a 20 ml aliquot of 20 drops per liter solution. This time we're going to add 40 milliliters of water. And so our total volume will be 60 mils. Since the volume increased from 20 mils to 60 mils by a factor of 3, therefore the concentration will decrease by a factor of 3 as well. So 20 over 60 is a dilution factor. It's a third. You multiply it by 20, and the final concentration is 6.7 drops per liter. Or if you prefer, you can get 60 over 20, which is 3 times. Take your initial concentration, 20 drops per liter, and divide it by 3, 6.7 drops per liter. Alright, beaker number 4. Another 20 ml aliquot of 20 drops per liter solution. This time we're going to add 60 milliliters of water. 20 plus 60 will give us a total volume of 80. The volume increases from 20 to 80, that's a factor of 4 times, so the concentration will decrease by a factor of 4 times. Take those two volumes, 20 and 80. 20 over 80 is a quarter. Multiply a quarter by the initial concentration of 20 drops per liter. The final concentration is 5 drops per liter. Or if you prefer, dilution factor is 80 over 20, it's 4 times. Your initial concentration is 20 drops per liter, divided by 4 is 5 drops per liter. You'll get it right every time. Don't memorize a formula. Okay, the last one. Take our last 20 ml aliquot, whatever's left there. This time we're going to add 80 milliliters of water. That'll bring our total volume up to 100 mils. So if we increase the volume from 20 to 100, we increase it by a factor of 5 times. Therefore, our concentration decreases by a factor of 5 times. The final concentration will be 20 drops per liter times 20 over 100, or 1/5, so that's 4 drops per liter. Or the final concentration is 20 drops per liter divided by 20 over 100, in other words, divided by 5, and it's 4 drops per liter. You'll get it right every time. Don't waste your time memorizing formulas. Just think logically. You'll get it right, guaranteed. Let's take just a moment to look at dilution calculations on a graph. Here's a plot of concentration versus volume. We started with 20 milliliters with a concentration of 20 drops per liter. We doubled the volume by a factor of 2 from 20 to 40, and that decreased the concentration by a factor of 2 from 20 drops per liter to 10. When we tripled the volume from 20 to 60, that reduced the concentration by a factor of 3 from 20 to 6.7. When we increased the volume by a factor of 4 from 20 mils to 80 mils, then the concentration decreased by a factor of 4 from 20 drops per liter down to 5 drops per liter, and so on. So this is an inverse relationship. As one variable increases, the other decreases proportionately. And this is the very same relationship that describes the pressure-volume relationship of gases, which I have plotted here. This is described by Boyle's law. Notice that as the pressure of a gas increases, its volume decreases proportionately. So in both these examples, you can solve problems involving dilutions or pressure and volume of a gas by making logical statements and making ratios that make sense, rather than memorizing formulas, and I would encourage you to do that. And that ends our study of the reaction rate experiment.